All right, so for problem number 1, I can see that it's a trinomial, so I'm interested to know, does it have a GCF that I can take out and then it's one of the easier trinomials, or is it one where there's still going to be a number left behind and I'm going to have to do the slide divide method? So between the numbers 7, 31, and 30, we have two prime numbers, 7 and 31, which means we're not going to be able to pull a number out as a GCF. However, we do have x to the third, x squared, and x, so you can actually pull an x out as a GCF, and that leaves 7x squared plus 31x plus 30. That leaves that behind. So now it's a pretty standard slide divide problem. We're going to do 7 multiplied by 30, and that gives us 210. And then we're looking for numbers that multiply to 210 but add to 31. And I will go ahead and leave that so that you can finish that problem. For problem 2, this has two terms. It's a binomial. So when I look at this one, I think, okay, maybe it's a GCF problem, maybe it's a difference of squares, maybe it's a sum or difference of cubes. And when I look at the numbers, those are not cubes. But this says m cubed right here, which makes me think it probably has a GCF, and then after that it's probably difference of cubes. So if you look at these, they're both even numbers. I can go ahead and take a 2 out. And we kind of lucked out because 2 ends up being the actual GCF. Like that's all you can take out. And the reason I can tell is because this is a perfect cube. 125 is 5 to the third. And that is a perfect cube. That's 4 to the third. But just in case you're not sure, you can go ahead and do the calculator trick. So 250 divided by x, 128 divided by x. If I hit graph, both are divisible by 1, but they stay the same. And then when you see that they're divisible by 2, you can see those perfect cubes in there. And then after that, you see decimals. That one's a decimal, but that one's 32, which is not a perfect cube anyway. This one's 50, which is not a perfect cube. That one's a decimal. And then you can see after that, we just get lots of decimals. 16 is a perfect square. These are perfect squares, but not perfect cubes. There's a perfect cube right there, but that one is not. So that's how we can kind of tell that 2 is the number we were supposed to take out, because when we see this 2 right here, that's where the two perfect cubes are. Okay, so I'm going to rewrite this problem with the 2 in the front. And then I'm going to say that my first term is something cubed minus something cubed. And so first I have 5m. And then second, I have 4. And if you've struggled with these problems, and I know a lot of you have, then it would be good for you to try using 2 different colors. It might make it a little bit easier for you. So 2, first set of parentheses, we're going to do the first term, keep the same sign, and then the second term. So 5m minus 4. And then for the next set of the parentheses, we do the first term multiplied by itself. So 5m times 5m. Then we do the opposite sign, so we're remembering SOAP. Same sign, opposite sign. And then we do the first term times the second term. So 5m times 4. And then after that, to finish up SOAP, we have same sign, opposite sign, and then we have always positive. And then we have the second number times itself. So if you do the colors, you can kind of see the pattern. We know SOAP, so we know to do the signs. We have the first term, the second term, first times itself, first times second, second times itself. So there's kind of a nice pattern there, and I think if you use the colors to do it, you might see that pattern more obviously. All right, so 2, 5m minus 4, that's 25m squared. 20m 4 times 4 is 16. All right, for this one right here, we have 18, 170, and 100. And so they're all even, so I can tell that they're all divisible by 2. 18 is the smallest number, so I'm going to think of numbers that divide into 18 and then check them with the other ones to see if they work. So 18 is divisible by 2. It's also divisible by 3, but 100 is not. It's also divisible by 6, but 100 is not. It's also divisible by 9, but 100 is not. So that means that the only GCF that we can take out here is that 2. So that leaves us with 9x squared minus 85. 85x minus 50. And then at this point we have a trinomial. It's got a 9 in front of the x squared. That makes it a slide divide problem. So 9 multiplied by negative 50 is negative 450. So we're multiplying to negative 450 and adding to negative 85. This problem is just a typical trinomial problem. You can see the x squared is already by itself. It's the exponent I would expect. There's nothing weird about this problem. So we can just go straight ahead and look for two numbers that multiply to negative 40 but add to 3. This problem is also a typical trinomial. It's almost ready to go. It doesn't have a number in the front, so I know there's no GCF that's a number. However, the exponent is wrong. We have n to the third, n to the second, and n. So that means we have a GCF of n that we can take out. N squared plus 14n plus 45. So we are looking for two numbers that multiply to 45 but add to 14. All right, over here we have a binomial. That's two terms. So whenever I work with binomials, I'm thinking, okay, maybe it's only a GCF problem, maybe it's difference of squares, maybe it's sum or difference of cubes. And if I look at this, I don't see an exponent squared, I don't see an exponent cubed. I do see some things in common though, so I'm certainly going to take the GCF and then see if there's anything else we could do with the problem. So between 6 and 18, I have a GCF of 6. Between x to the fourth and x, my smallest exponent is just this x because that's kind of like x to the 1, and so that's what I'm going to take out. All right, now that I've done that, I took out the 6 already. I had x to the fourth, so now I'm going to have x cubed left over. And then 18 divided by 6 is 3. I took the x out already, so I'm done. Now this almost looks like sum of cubes. I have x to the third plus a number. However, that number is not a perfect cube, so I'm not going to keep factoring it. No need to do it if it's not a cube. All right, for 7, again, I have a binomial. That's two terms. So I'm going to think, okay, maybe it's only a GCF problem, maybe it's difference of squares, maybe it's sum or difference of cubes. And then when I look at the problem, I see m squared. So that triggers my brain to think, okay, maybe it's difference of squares. And then when I look at the two numbers 4 and 9, those are both perfect squares. So this is a difference of squares problem. That means I have two sets of parentheses, one with a plus, one with a minus. The square root of 4 is 2, so I'm going to put a 2 and a 2. The square root of m squared is m, so I have an m and an m. The square root of 9 is 3, and I'm done. All right, for a problem like this, when you see that many things going on, that's pretty much always just going to be a GCF problem. So I'm looking at the negative 25 and the negative 5. I know that if the leading term like this has a negative in the front, then I'm going to take that out with my GCF. So now I'm comparing the numbers. 25 and 5, my GCF there would be 5. Between x to the 4th and x to the 5th, x to the 4th is smaller, so that's what I'm going to take out. Between y to the 3rd and y to the 5th, y to the 3rd is smaller, so that's what I'm going to take out. All right, so negative 25 divided by negative 5 is 5. I had an x to the 4th, I took it out. I had a y to the 3rd, I took it out. So 5 is all I need for the first term. For the second term, I have negative 5 divided by negative 5. That's going to give me a positive. And since I already took the 5 out, I don't really need to write anything. X to the 5th, I took out x to the 4th, so I need 1 more. Y to the 5th, I took out y to the 3rd, so I need 2. So xy squared. This doesn't look like anything. That doesn't look like difference of squares. That doesn't look like sum or difference of cubes. It's not a trinomial. So that's how I know that I'm done.